All right, Chem 11. Today's topic, limiting reagent and maximum yield. All right. And we're also going to learn about cheese sandwiches today, which is awesome. To do this lesson, there are some practice problems at the end of the lesson, so you'll need your Calculator-O-Matic 3000 Solar Edition. So the lights go out. This guy's still doing chemistry. You'll need your Periodic Table-O-Matic 3000 Mendeleev Edition for those molar masses that everyone loves. All right, so limiting reagent and maximum yield. This is a big concept in chemistry, but it's actually very, very easy. All right, but before we talk about any chemistry, we're going to talk about cheese sandwiches. All right, hence our little title header here: bread, cheese, ching, money. All right, so the perfect cheese sandwich. All right. The recipe for the perfect cheese sandwich is as follows. Pay attention. This is how you get paid. 2 pieces of bread. 1, 2. 1 slice of cheese right here. And that makes the perfect cheese sandwich. Boom. Money. So it would kind of look like this in terms of, if we use pictures. Kind of like what I have here. Now, 2 pieces of bread. 1 slice of cheese. 1 sandwich, 2 pieces of bread, 1 slice of cheese. I am not the greatest artist. You probably noticed that. So I'm going to draw a $sign for sandwich. 1, because it's an S for sandwich. And 2, people will get paid for my cheese sandwiches because they are awesome. They will pay for those things. So if we were to show that as a, we said chemical reactions, chemical equations are like recipes. The recipe for a cheese sandwich would look kind of like this, right? It would be 2B plus 1C, I don't have to show the 1, and my sandwich would be B2C, right? This compound would be the sandwich. There's my slice of cheese, there's my 2 breads, all right? No big stretch of the imagination. In terms of chemistry, this is my recipe or chemical equation to make a cheese sandwich. All right? And for those of you out there, right, some people will take 1 slice of bread, right? They take 1 slice of bread, and then they take the 1 slice of cheese, and they put that, and then they pull this little piece of magic right here. They fold the bread over like that, the single piece of bread, and a single piece of cheese, and they fold over and say, that's a sandwich. Don't you ever have me over and tell me this is a sandwich. All right? It's not going to happen, right? This is a disgrace. This is a good sandwich. This folded over thing, not a real sandwich. What am I, 3? Right? Don't ever bring me in something like that. All right? Just being forewarned. All right? No foldy single slice sandwiches. Good God. We are civilized people here. All right. So back to the good sandwiches. You're a master chef. Your cheese sandwich takes off. People are loving it. They want to throw money at you left and right here. Can I order some? Can I buy some off of you? Yeah. Orders are coming in left, right, and center, right? One order comes in, 15 sandwiches. Well, what would you need for 15 sandwiches? So if I needed 15 sandwiches, right? If I needed 15 of these, what would I need? Right? This is a sandwich. I need 15. You can do that in your head. You're already probably thinking, sir, you'd need 30 slices of bread and you'd need 15 slices of cheese, and that would give you the 15 sandwiches, right? And if you look at it, that relationship is the same. Up here we have a 2 to 1 to 1 relationship. And look here, 2 to 1 to 1 relationship. That relationship is the mole ratio. We've talked about the mole ratio before. And that's basically what you did in your head. 15 sandwiches, well, each sandwich needs 2 breads, so 15 would require 30. Each sandwich has 1 thick slice of cheese, so 15 cheeses for 15 sandwiches. Boom, done. Out the door, you just got paid. That's awesome. Right? So all you did was use some stoichiometry in your head and the recipe for the sandwich. This thing right here. And you figured out that we need 30 bread, 15 cheese for 15 sandwiches. What if an order came in for 42 sandwiches? So now I need 42 sandwiches. Well, what would I need there? Well, my relationship of cheese per sandwich is a 1-to-1. So whatever my sandwich is, my cheese is the same. I'd need 42 slices of cheese. And my relationship of bread to sandwiches is 1 sandwich, 2 breads. So I would double that amount. 42 now becomes 84 bread. If I had 84 slices of bread, 42 slices of cheese, I can make 42 sandwiches and make, ching, a whole bunch of more money, right? So now I'm getting paid. Your business starts to take off, right? You hire your best friend because so many sandwiches are flying out the door. Sorry, bread. Took the bottom off you there. So sandwiches are flying out the door. You're expanding. You're becoming the sandwich king or queen of Toronto. You hire your friend, right? They're a rookie. Your supplies of bread and cheese are getting used up because more and more sandwiches are going out the door. And at the end of the day, right, you end up with 10 slices of bread. I know I'm not drawing these nearly as nice as my original breads, but you get them. So I got 10 slices of bread and I've got 10 slices of cheese. And that's all you have left, but it's almost closing time. I've got my 10 bread and my 10 cheese. It's almost closing time. I think I'm just going to make it. The delivery van comes in the morning and it'll have lots of bread and lots of cheese and I can make more cheese sandwiches and keep getting paid. The phone rings. An order comes in late. Your friend, that rookie, picks it up and tells the client it'll be no problem. The order's for 10 sandwiches. And your rookie, your friend says, "Oh, that's easy, I got that. 10 sandwiches, got it." You scream no. No! As they're hanging up the phone. Why did you scream no? Right? The order came in for 10 sandwiches. Your friend, who didn't know chemistry, said no problem. And you told them, wait a second, rookie, there is a big problem here. What's the problem? Think about it in your head right now for a moment. All right? You're probably saying, I don't know if we have enough bread. So here I've got my 10 bread and my 10 slices of cheese, just like here. And what will happen is we'll make that first sandwich. The bread pile goes down a bit, goes down by 2. The cheese pile goes down by 1. So after the first sandwich, and I'll just put the $sign for the sandwich because, again, boom, 1 sandwich, and we used up 2 bread and 1 cheese. Made a sandwich right there. You go to make a second sandwich, 2 bread, 1 cheese, boom, sandwich. 2 bread, 1 cheese. Another sandwich. We've got 2 sandwiches now, just like on the screen over here. That third sandwich gets made. 2 more bread, 1 more cheese. A fourth sandwich, 2 bread and a cheese get taken, turned into a sandwich. 2 more bread, 1 more cheese. Fourth sandwich. And then you make that 5th sandwich. 2 bread, 1 cheese, 5th sandwich. Right? So we've got our 5 sandwiches here, but the order was for 10. And I've got 1, 2, 3, 4, 5. Your friend says, hey, where's the next sandwich? And you're looking at them going, well, that was the problem. 10 bread can only allow me to make 5 sandwiches. 1, 2, 3, 4, 5. After the fifth sandwich is put onto the sandwich plate, the bread plate is empty. We can see it's empty here. We can see it's empty here. The cheese plate still has 1, 2, 3, 4, 5. And again, if you could see this up close, there'd be 5 slices of cheese there. And that was why you yelled no to your friend when they took that order. You knew the recipe. I need 2 bread and 1 cheese. If I have 10 slices of bread, I can only make 5 sandwiches. That's only half the order. So now you got to call that client back and beg their forgiveness and say, look, we kind of made a mistake here, a rookie mistake. The cheese plate will still, yes, it'll still have 5 slices of cheese. And truth be told, you could still make the 10 sandwiches with the cheese, but the bread ran out. The bread gets used up quicker than the cheese, or gets used up at a greater ratio. 2 of these for every 1 of those. Right? So, what are we going to do? We got an issue here. Right? The problem was, we go back to that recipe, you use up a greater amount of bread than you do cheese every time you run the reaction. Right? 2 of these for 1 of those to make 1 of these sandwiches. So the bread starts to go down quicker than the cheese. It gets used up quicker if you think about it that way. Right? And there's our reaction again. I need 2 amounts of bread for every 1 amount of cheese per sandwich. All right? So the bread gets used up at a 2-to-1 ratio. If we use mole ratios, it's a 2-to-1 ratio to the cheese when it comes to making a sandwich. After the 5th sandwich, all the bread is gone. The bread plate is empty. No more sandwiches. The most sandwiches you can make with 10 bread and 10 cheese is 5. That's it. No more. Right? So, let's talk about chemistry now. I'm hungry because of all the sandwich talk, but let's talk about some chemistry. All right? This brings us to the idea of the limiting reagent. Right? After the 5th sandwich, all the bread's used up. The bread plate is empty. No more sandwiches could be made. It's impossible. All my bread, it's all crossed out here. It's all gone. 5 sandwiches. That was it. The cheese plate still had 5 slices on it. Therefore, the bread is the limiting reagent, while the cheese is the excess reagent. All right? Bread is limiting reagent. Cheese is excess reagent. What is that? Well, the limiting reagent is the reactant in a reaction. We know the reactant is the starting material, so the cheese and the bread, that gets consumed up in its entirety first out of all the reactants. All right, so we had 2 reactants, bread, cheese. This one got used up first. It is my limiting reagent. Right? When all of this is gone, the reaction, and in our example, the reaction is bread, sandwich making, the sandwich making stops. I don't have this, and I need this to make a sandwich. So when I run out of this, I've hit my maximum yield of that. The reaction will stop at that point, just like the assembly line of making sandwiches stops at that point. The excess reagent is the reactant that only gets partially consumed when the reaction runs. I only used up some of the cheese, not all of it. I've still got these 5 slices right here. The reaction has stopped though because I'm out of bread, and my cheese plate still had 5 extra slices of cheese on it. The cheese is my excess reagent in this example. The bread is my limiting reagent. The bread limited how much product I could make. The maximum yield. The maximum yield for a chemical reaction is the amount of product that is being made when the limiting reagent is consumed entirely. So in the 5th sandwich, because we said we can make 5 sandwiches, when this 5th one was made, the last 2 bread were used up. So our maximum yield, given these amounts of reactants, was 5 sandwiches. 1, 2, 3, 4, 5. That's it. The reaction stops once one of these is gone, the limiting reactant, and whatever product you have, that's it. That's all you can make. You've reached your maximum given these reactants. So you've made as much as you can. You've reached the maximum yield. 5 sandwiches is our maximum yield if we have 10 bread and 10 cheese. All right, so let's see how this applies to real chemistry. I hope that kind of made sense. You were probably able to do that math in your head, the cheese sandwich, that's why I use it. But let's do some real chemistry now and see how it applies to what we already know. And you'll find that there's a lot of tiebacks to things that we've already done, which is great. Because if you're okay with what we've done so far, you're going to fly through this. The cheese sandwich. I am eating after I finish this video. All right. I'm going to use up all of the board here. And this is where your calculator and your periodic table will be needed. So I have 3 example questions. I'll go through them nice and slow. I'll talk out loud as to what my brain would be thinking internally while I go through the problem. So example number 1. Sodium metal reacts with chlorine gas to produce solid sodium chloride according to the following balanced equation. So it's always nice to have the recipe right off the bat. It says, A, determine the limiting reagent if 4.80 moles of sodium reacts with 2.7 moles of chlorine gas, and B, what amount of salt will be made in the reaction. All right, now on the side, I've got my steps to solve, all right? And I'm gonna have to make an adjustment here because balanced equation should be first. I should switch these two. But my steps to solving are here. I'll speak them out anyway. I'm gonna move this so I have all of the room, and I'll bring that back in when we gotta do our next equation. So I've got Na, blue marker is running out, chlorine gas, and sodium chloride. To balance that out, I have 2 chlorines, only 1 here, so a 2 will go there, and then I've got to put a 2 in front of the Na. The first thing I need always is a balanced chemical equation. I have that now. All right? Excuse me. So the first question was, determine the limiting reagent if 4.8 moles of this reacts with 2.70 moles of that. All right, so now I have to determine the limiting reagent. This is a new step. It uses some stuff we've already done, but this is a new step. Now, if these are masses, I would have to turn these both into moles, but they're already in moles here, so I get off a little bit easy. So since they're both in moles, I am now going to find my limiting reagent, and I'm going to use my mole ratio to do that. Now, once both my reactants are in moles, I always bring this one over this way. All right, you can do it both ways, and I'll show you both ways just to get it done and show you that it's not always a one-sided thing. So I'm going to bring all of this over, right? And before I do that, I should indicate that this is what I got, right? I got this, and I got that, right? I know it's half, but I like to say got. So I got this much of that, I got that much of that, all right? That's what I actually have in my possession. So if all 4.8 moles of the sodium was to be consumed, so how much sodium do we got? We got 4.8 moles. If all of that gets consumed, how much chlorine would be required? I multiply it by my mole ratio. Now I know there's a little 1 here. I'll draw it in, even though you don't really need it. And head over heels, it's this. So my mole ratio is there. And that equals 2.4. Oh, sorry, I did head over heels wrong. Yikes, good catch, sir. The head of the arrow is at the 1. The heel of the arrow is at the 2. And that yields 2.4 moles of chlorine gas. So this is what I need. So if I'm going to burn off all 4.8 moles of this sodium, I need 2.4 moles. I need 2.4 moles. Well, how much chlorine do I got? I got 2.7. I got more than that. So I can burn off all 4.8 can get burned off, and I'll only need 2.4 moles of chlorine. I have more than 2.4 moles. That means that my sodium is my limiting reagent. And so what I do is I write LIM above that, and this one gets EX. All right? Sodium is the limiting reagent because when all 4.8 moles gets burned off, I'll burn off 2.4 moles of chlorine. Well, I've got 2.7. All this is gone, and I still will have some of this left over. This one is gone. This one will have 0.3 moles left over. And so it's excess. This is lim. Now, what if I did it the other way? I'll do it in this color just to show you. What if I went this way with it? So what if I took that and went over there? Right? 2.7 moles of chlorine gas, and I bring it over here. 2.70 moles times my mole ratio. In this case, it's going to be 2/1. And that ends up being 5.4 moles. And that's what I would need. So now look at it this way. If we do it this way. So to answer this question, you're either doing the pink or the brown. Both ways will give you the way to do it. What I said here in the brown work, 2.7 moles of chlorine gas. If it all gets used up, I'll need 5.4 moles of sodium. I only have 4.8. I don't have enough sodium. Right? This is what I need. This is what I actually got. 4.8, right? I took it down here. So I need more than I got. To burn off 2.7 of this, I need 5.4. I've only got 4.8. That's not enough. So this is my limiting reagent. Whether I do it the pink way or the brown way, it still says sodium runs out first. All right? Pause the video if you want to get that down. I'm going to erase this brown calculation because we only need the one. So I've proven that I've got enough information here that tells me sodium is my limiting reagent. So I'm going to get rid of that. But you can see it worked out both ways. I can explain it. Now the second one said, what amounts of this can I make? And I know amount in chemistry is moles. So, to find out the maximum amount of product I can make, I use the limiting reagent every time. This is going to run out first, so I'm going to use this. It's like our bread and our cheese. The bread ran out first, all right? I knew bread would run out first, so I used bread to figure out how many sandwiches it was going to make. Same thing here. I'll do this one in green. I bring this over. So this is part B of that question. This was part A. And 4.80 moles comes over, and I multiply it by the mole ratio. And the mole ratio, if I look at it, is 2/2. Nice and easy. And that still is 4.80 moles, because 2/2 is 1, of NaCl. And that is my final answer, because it said amount. If it said mass, right, I would then multiply that by the molar mass and turn it into grams. But it said amount, and amount in chem is moles. All right, so that's number one answered. All right, pause the video right now if you need to get that down. I'm going to set up our second example. All right, example number 2. Example number 2 says, Copper 1 sulfide is produced as shown below. So I've got my recipe already here. It says determine the limiting reagent when 85 grams of copper reacts with 30 grams of sulfur. So I've got masses here of each of my reactants. And calculate the maximum yield. Maximum yield is mass. So grams of the copper 1 sulfide that can be produced. So let's do that. You can get that question down, or you can have it as I work it out here. And again, we'll start off with our balanced equation. That's the number one thing. Cu plus S yields Cu2S. And to balance this off, I can see that I'm going to need 2 coppers, and I believe that's it. 2 copper, 1 sulfur, 1 sulfur. The first thing, balanced equation, got it. And it said I have 85 grams of copper and 30 grams of that. A is find the limiting reagent, and B was what is my maximum yield? So what mass of that product can be produced from this? All right, so I'll do A in pink here. I want to relate these two things and find out what's my limiting reagent. But I can't relate them because this relates in moles. The 2 to 1 to 1, that's the mole ratio. 2, 1, 1. That's my mole ratio, not the mass ratio. These are masses. I have to turn those into moles first. So I divide by the molar mass on the periodic table, right? And the molar mass for copper is 6355. And the molar mass for sulfur, I always see I stretched it out more because I know I'm going to be working in my columns. And the molar mass for sulfur is 32.07. So I divide each element. Now for copper, I only used, there's 1 copper here, I used 1. This 2 is part of my mole ratio. So it's not 2 63s, it's only 1. That copper right there is 63. I do not use the 2. Remember, we talked about that already. When I divide this out, it's 1.34 moles. When I divide this one out, it is 0.935 moles. All right? And this is what I got. All right? I actually got 85 grams of this, which is 1.34 moles. I actually got 30 grams of that, which is 0.935 moles. Now I'm going to figure out my limiting reagent. Again, I always take the first one and bring it over. You can do it both ways. We showed you that before. So 1.34 moles. If I use up all 1.34 moles of the copper, how much sulfur will I need? So to bring it over, I multiply it by the mole ratio, which head over heels is 1/2. And it ends up being 0.67 moles. This is what I need. All right? I've got this and I've got this. To burn off all of my copper, and I have 1.34 moles of it, to burn off all of those 1.34 moles of copper, I need 0.67 moles of sulfur. Well, I got 0.9, right? 0.935. I've got way more than I need. So that means this is my excess reagent. That E came out very bad. I apologize for that. And this is my limiting reagent, the copper. Again, if I do it the other way really, really quick, 0.935 moles, and I take it over, ooh, bad arrowhead, not very good at all, 0.935 moles times 2/1, and I do that one out, I end up with 1.87 moles. So to burn off all the sulfur, I need 1.87 moles of the copper. I have lower than 1.87 moles, so I'm not going to be able to burn off all the sulfur. That means it's excess, and I'll run out of this. I only got 1.34, I need 1.87. So both ways will point to copper being your limiting reagent. I'm going to get rid of that, but just to show that it doesn't always have to go this way, I do that. You can go this way and still get the same answer. So my limiting reagent is the copper. All right? Cu is my limiting reagent. So now it wants the maximum yield. We're doing part B, the maximum yield of the copper 1 sulfide, or sulfide, sorry. I'll do that in red. I use my limiting reagent because this is the one that's going to run out first, like our bread in the previous example. So I bring that over. 1.34 moles is what I have. And I multiply it by the mole ratio. The mole ratio is 1/2. And that is 0.67 moles of the copper 1 sulfide, but I need the mass. So now I'm going to multiply this by the molar mass of this. So I take 2 C's and an S and I add them together, and I end up with 159.17 grams per mole. When I multiply that, I'll end up with 106.64 grams of the copper 1 sulfide. That is my maximum yield. All right? This is my final answer for B. So A, copper was the limiting reagent. B, my maximum yield is 106.64 grams of copper 1 sulfide. All right? No problems. I'll leave that up for a moment. Pause the video if you need to get that down or take a second look at it. I'm going to do our last problem. All right. Example 3. Wow, okay, there's a lot to it. 4 parts. Phosphorus and oxygen gas react to form diphosphorus pentoxide. Write the balanced chemical equation. So they do not give me the recipe. I have to figure that out. If you reacted 100 grams of each substance, what's your limiting reagent? What is the maximum yield of the product? And then what mass of the excess reagent will remain unreacted once the reaction is over? That's like the cheese. It's like saying how much cheese would remain unreacted or not in a sandwich from before. And you guys would have been able to tell me, oh, you're going to end up with 5 slices of cheese left over. So that's what this is asking, D. How much of that excess reagent will be left over because the other thing is run out and there's nothing to react with? All right. So let's take a look at this one. And it says phosphorus plus oxygen gas gives me diphosphorus pentaoxide, and I have to balance that out. So this one gets a little bit tricky. I'll need 4 of these, 2 of these, and 5 of those to balance this off. So there's A done. A was, give me the balanced chemical equation. This is it right here. B said, if I have 100 grams of each reactant, if I have 100 grams of each reactant, what's my limiting reagent? So I have the same amount. You think, oh, well, they should combine equally, but we know that's not the case. Before we had 10 bread and 10 cheese and realized one gets used up sooner than the other. So we have the same mass, 100 grams, 100 grams. So we have to find our limiting reagent. So to do that, I've got to convert them into moles. This balanced chemical equation relates in moles. These are masses. So I have to turn them into moles first. So I'm going to divide by the molar mass of each element. Now, for the phosphorus, if I go to my periodic table, it's 30.97. Not for phosphorus, just this, just the formula. That coefficient's part of my mole ratio. This is not for phosphorus, it's 1, because that's all the green part is. Here, I've got oxygen gas. So I've got 2 oxygens, so it's 16 and 16, which is 32. I divide those out, and I get 3.23 moles of this, and end up with 3.125 moles of that. This is what I got. I got this. That and that are what I'm actually working with. I want to find out which one is going to run out first. Again, I take the first one and bring it over. It's just the way that I've always done it. So I take the 3.23 moles and multiply it by the mole ratio. The mole ratio is head over heels. The head of the arrow's at the 5. The heel of the arrow's back at the 4. And when I do that, it ends up being 4.04 moles of oxygen gas. And this is what I need. So what I've done here is I said, if I use up all of my phosphorus, all 3.23 moles, how much oxygen would I need? I need 4.04 moles of oxygen. Well, how much do you got? Well, I only have a little over 3, and I need 4. I don't have enough. So that means that oxygen is my limiting reagent, and phosphorus is my excess reagent. All right? So my limiting reagent now is the oxygen. That's the answer for B. All right? I always write it above here, so future calculations, I can see what my limiting and my excess is. Part C was the maximum yield of this. And we know that that's in grams. So what I have to use is what I got. Now here's a common mistake. Pay attention. I've got 2 moles worked out for oxygen. All right, my oxygen gas, I've got this. And I worked out this. This says moles of oxygen. What one do I use to find my maximum yield? I use this one because this is what I actually got. I don't have this. This is what I needed to react with all of this. This is what I actually have. 100 grams of oxygen is this. So this is what I use, not this. This is what I use to bring over and figure it out. It's my limiting reagent. I use how much I actually have of it. So 3.125 moles times my mole ratio. My mole ratio, the head of the arrow is at the 2, the heel is at the 5. And when I multiply that, I end up with 1.25 moles of the diphosphorus pentaoxide, but it wants maximum yield in grams. That's not grams, so I've got to multiply by the molar mass. So again, I just take the formula. This 2 got used up right here. That 2's gone. It's this. 2 phosphorus, 5 oxygens. When I add that up on the periodic table, it's 141.94 grams per mole. I multiply these 2 numbers, my moles will cancel, and I'll be left with grams, and it will be 177.425, I didn't round off, grams of the P2O5. And that is the final answer for C. All right? So A was the equation. B was what is my limiting reagent. I found out it was oxygen. C is my maximum yield in grams right here. Now, I'm going to have to erase this to do part D. So pause the video, get this down if you need it. I'm about to erase it. All right? So, for D, I don't need any of this. Everything I need for D is right here. I'm going to keep these molar amounts because now I have to figure out how much of this was left over. I'm going to use a different color. I'm going to use D, is going to be done in green. So I know that this is my limiting reagent. So this one's going to get all used up. I'll have some of this left over. So I'm going to bring that over here and see how much of this actually gets used up when all of my limiting reagent is gone. So 3.125 moles times that mole ratio. The mole ratio, the head of the arrow is where there's a 4. Over the heel of the arrow is where there's a 5 as far as the coefficients go. And I will need 2.5 moles, and that's what I'll need. That's of phosphorus. All of this gets used up. I already proved it. It's my limiting reagent. When all of this is gone, I will have used up 2.5 moles of phosphorus. All right? I need 2.5 moles when all this is gone. I've got 3.23 moles of it. So now what I'm going to do is I'm going to take this, what I have, and subtract what gets used up when I burn this off. So I'm going to take 3.23 moles, right? This is how much I got, and I'm going to subtract what I used up, or what I needed, and that's 2.5 moles, and that equals 'Sorry, I can do this different. I'm going to do this the same way. All right, so I'm going to show you two ways of doing this. One is this way. So I take 3.23 and I subtract 2.5, and that equals 0.73 moles of the phosphorus that's unreacted. And then I simply multiply that by 30.97 grams per mole, and that will give me grams of phosphorus. All right? And that ends up being 22.61 grams of phosphorus. All right? So this is how much phosphorus, this is the answer for D, this is how much phosphorus is left over. It is unreacted because all of the oxygen will be gone. All right? So that's what you can do there, or I'll show you a second way. All right? So if you understood this, good. The other way would be I take this, the 2.5, and I multiply it by 30.97 grams per mole, the molar mass of the phosphorus, and that would equal 77.4 grams, and that's what would be used up. Then I can take the 100 grams that I had and subtract the 77.4 grams, and I still would end up with 22.6. Either way, the dark green way or the light green way, they'll both get you this same answer, which is the proper answer. All right, so what I did there, the second way was, I said, well, this is how much is going to get used up when all of this is gone. I multiplied it by its molar mass, 30.97. It means I used up 77.4 grams. I started with 100 grams, so I subtract the 77.4. I get 22.6. The other way, the first way I did it, I took the number of moles that I got, subtracted what I needed from it, found out how many moles were unreacted, and then multiplied it by the molar mass and got the same answer. So if you want to do it this way or this way, it'll still get you the same answer. Anyway, that's everything. Pause the video right now. We've reached the end of the lecture. But pause the video, get this down if you want. Again, for part D, the dark green way or the light green way, they'll both get you this, both get you there. So we've answered all 4 of our questions, and then that's it. And I found, again, we've been using memes at the end of things. So this is a famous one where the guy's looking at the other girl there. And this is our 2-slice cheese sandwich. There's you, and there's the 1-slice cheese sandwich, right? Anyway, I thought that was kind of funny. That's the end of our lecture. Hope you understood it. If you have any questions, please comment in the comment section of this YouTube video or reach out to me through Edsby. All right, talk to you later. Bye-bye.